When scientists search for alien life, they look at planets. Specifically, they look at planets in what they call the habitable zone, the narrow band of orbital distances around a star where temperatures allow liquid water to exist on a rocky surface. This is the framework that has guided astrobiology for decades, and it makes intuitive sense. Life as we know it needs water. Water needs the right temperature. The right temperature requires the right distance from a star, so we search the planets and ignore everything else. But there is a physicist at the City University of New York who published a paper arguing that this framework, while not wrong, may be missing something. Not a planet somewhere we haven't looked, something much closer, something so obvious that nobody thought to look there. The star itself? What if the most common objects in the universe, the billion-degree nuclear furnaces that every inhabited planet orbits around, are not just energy sources for life, but habitats for it? What if some of the stars we have been cataloging for centuries are not just hosts to life on their surrounding planets, but home to something living inside them? This is not science fiction. It is a peer-reviewed physics paper, with a testable prediction, published in a respected journal, by researchers at a legitimate university. And what it says about the universe is something that the conventional framework of astrobiology was never designed to consider. Start with the obvious objection, because it is the right place to start. The interior of a star is not a gentle environment. The core of our own sun reaches temperatures of approximately 27 million degrees Fahrenheit. The pressure at the core is roughly 250 billion times atmospheric pressure at Earth's surface. Every atom in the solar interior is stripped of its electrons and exists as a naked nucleus moving at velocities that would be described as extreme by any physicist's standards. No chemical bond could survive there. No molecule, as we understand molecules, could hold together. No water, no carbon chains, no proteins, no cell membranas, no chemistry of any kind that has ever been associated with life on Earth could exist for a fraction of a second in the interior of a star. This is not a matter of debate. It is basic physics. But here is where Louis Anchordoqui and Eugene Chudnovsky, the physicists at the City University of New York, who published the nuclear life paper in Letters in High-Energy Physics, start from a different set of assumptions. They do not propose that life inside a star would be chemical. They propose that it might be nuclear, and the distinction is not trivial. Chemical life stores and processes information in the arrangement of atoms and molecules. Nuclear life, if it exists, would store and process information in the arrangement of subatomic particles, at energy scales and at distances so much smaller than chemistry that the two types of life would be as different from each other as a living cell is from a galaxy. The question they asked was not whether chemical life could survive in a star. That answer is obviously no. The question they asked was whether any physical system capable of storing, copying, and evolving information could exist in the nuclear environment of a stellar interior. And their answer, hedged carefully and speculatively but grounded in real particle physics, was that it might. The specific mechanism they proposed depends on two hypothetical but theoretically motivated physical objects. The first is cosmic strings, which are not the strings of string theory but rather hypothetical one-dimensional defects in the fabric of spacetime that may have formed in the extremely early universe as it underwent phase transitions during the creation of matter. The second is magnetic monopoles, particles that have only one magnetic pole rather than the two poles of every known magnetic particle. Neither cosmic strings nor magnetic monopoles have been directly observed, but theoretical physics gives them real credibility, and their existence is not ruled out by anything we currently know. The argument goes like this. Magnetic monopoles, if they exist, would naturally cluster along cosmic strings. Stars, through their gravity, could capture these strings and draw them into the stellar interior. Once inside a stellar core, the turbulent motion of nuclei through the plasma would cause these beaded strings, monopoles strung along cosmic strings like beads on a necklace, to entangle. The entanglement process could allow them to encode information in the pattern of their arrangement. And if the strings could replicate this encoded information, the way DNA replicates genetic information, then you would have a physical system that meets the minimum definition of life. Not life as we know it. Life as physics, operating at the nuclear scale, in an environment that is lethal to everything we have ever classified as living. The researchers themselves are careful. They describe the scenario as speculative, unprovable with current technology, and dependent on physical objects that have not been confirmed to exist. But they include something in the paper that elevates it above pure speculation. They include a prediction. They argue that if nuclear life exists inside stars, it would consume some of its host star's energy to sustain and replicate itself. This consumption would cause the star to cool slightly faster than stellar physics alone would predict, and this effect would be detectable. Some stars, when analyzed against the standard models of stellar evolution, do show anomalous cooling rates that the models cannot account for. The researchers do not claim these stars are necessarily hosting nuclear life, but they point to the anomaly as a place where the hypothesis could in principle be tested, and as a reminder that the universe has already provided data points that fit the prediction. Before the prediction was widely discussed, while the nuclear life hypothesis operates at the subatomic level, there is a completely different category of star-based life that operates at the other end of the scale. not inside stars, but around them. For 60 years, physicists have discussed the possibility that a sufficiently advanced civilization might build a structure around its star to capture essentially all of its energy output. Freeman Dyson proposed this idea in 1960, and it has been called the Dyson sphere ever since, though Dyson himself envisioned it less as a solid shell and more as a vast swarm of individual, energy-collecting structures orbiting in configurations that, from outside, would appear to envelop the star. A civilization that had built such a structure would be almost unimaginably powerful by human standards. It would be capturing the full output of an entire stellar engine, quadrillions of watts of continuous power, to run whatever systems, computations, and activities it had decided to devote itself to, and it would be doing it from inside the structure, living in an environment that from the outside would look like a star that was behaving strangely, emitting unusual heat in unusual patterns and flickering in ways that normal stellar physics could not explain. In July of 2026, a new study published results that specifically addressed where these structures would most plausibly be found and what signatures they would leave. The research found that red dwarf stars, the most common type of star in the entire Milky Way, are actually the most attractive candidates for Dyson sphere construction. Red dwarfs are small and cool enough that the amount of material needed to build an energy-capturing swarm around one is far smaller than what would be needed around a larger star like our Sun. A swarm built around a red dwarf could orbit at distances between roughly 5 and 30% of the Earth-Sun distance, close enough that a relatively modest construction effort would still capture an enormous fraction of the star's output. The study also flagged white dwarfs, the dense remnants of dead stars like our Sun, as promising candidates. White dwarfs are extraordinarily dense, packing the mass of a sun into a sphere roughly the size of Earth, and they emit energy that could be harvested by orbiting structures at very close range. A Dyson swarm around a white dwarf would be detectable by its infrared signature, emitting waste heat in a pattern that would distinguish it from natural stellar objects. The study identified specific observational signatures that would separate a natural star from a star surrounded by artificial energy harvesting structures, essentially a search blueprint that could be applied to existing and future telescope data. And then there is Tabby star, officially designated KIC 8,462,852. It sits roughly 1,480 light-years from Earth in the constellation Cygnus. It is a star that, over the course of years of observation by the Kepler Space Telescope, dimmed and brightened in patterns so complex and so irregular that no conventional astronomical explanation has fully accounted for it. Cometary dust clouds have been proposed, circumstellar debris, gravitational interactions with other objects. None of these explanations has achieved consensus. The pattern of dimming is not the regular, predictable pattern of a planet passing in front of a star. It is irregular. Sometimes the star dims by 22%, sometimes by fractions of that. The pattern changes over months in ways that natural mechanisms struggle to predict. When the anomaly was first announced in 2015, Jason Wright, an astronomer at Penn State and one of the leading researchers in the search for alien megastructures, said publicly that the observed behavior is consistent with what you would expect from a Dyson sphere construction project in progress, with large structures partially but not fully enclosing the star and creating variable obstruction of its light as they move in their orbits. He was careful to say this was not his preferred explanation. He considered it a hypothesis of last resort, but it was a hypothesis that the data at the time did not definitively rule out. Subsequent observations in different wavelengths, combined with detailed spectral analysis, have pointed increasingly toward circumstellar dust as the most likely explanation. But the dust explanation is itself not fully characterized, and the star's behavior continues to generate new papers in the literature. The intersection of these ideas, nuclear life in stellar interiors, plasma-based organized systems in stellar atmospheres, Dyson spheres harvesting stellar energy, and the unexplained behavior of stars like Tabby's, forms a coherent picture of why stars themselves, and not just the planets around them, deserve to be part of the serious scientific conversation about where life and intelligence might exist. The nuclear life hypothesis reminds us that life's fundamental requirement is not chemistry, but information processing, and that information processing is not limited to carbon-based molecular systems. The Dyson sphere research reminds us that the most advanced civilizations might not live on planets at all, but in engineered environments that look to outside observers like oddly behaving stars. And the unexplained stellar anomalies remind us that there are already objects in the sky whose behavior our physics cannot fully account for, sitting in the database of every major observatory, waiting for an explanation that may or may not be mundane.